In this lecture we will start the basic approach, one of the basic approach in nonlinear modeling of structures, and that is the lumped plasticity approach or concentrated plasticity approach. So before I actually start that demonstration, I want to emphasize the importance of this particular book, Modeling for Structural Analysis by Graham H. Powell. Professor Graham Powell is the author of a very famous program, structural analysis program for nonlinear modeling and analysis called Perform 3D. So it is a product of computers and structures, Perform 3D. So I will be referring to this program many times during this demonstration also. So although I will be discussing mainly in the context of e-tabs, but this is a specialized program. If someone can spend time to learn that, that is far more stable and more detailed for performance based analysis and nonlinear analysis for structures. So please check that book. It covers many of the important concepts related to nonlinear analysis, nonlinear modeling. And one more reference before I actually start. I developed this tutorial document actually using the help of some of my previous thesis students, and this document can be downloaded from this reference. It is not directly step-by-step tutorial for nonlinear modeling and analysis using e-tabs. It actually gives the basic input, the source of all required parameters, and the overall procedure for nonlinear modeling using e-tabs 2016 onwards. So many of the major features of nonlinear modeling and analysis were introduced in version 2016 onwards, right? So currently we also have version 2020, but from 16 onwards it's mostly the features are same, although with every new feature, with every new version, more of the nonlinear modeling and analysis capabilities are being implemented in e-tabs. So e-tabs will soon become the flagship program from CSI. But still many of the practicing engineers which are in the domain of performance based design, they prefer Perform 3D over e-tabs because of its simplicity, and it is also more stable. The analysis engine, it have very less issues related to convergence when compared with more detailed e-tabs. So in last lecture we discussed that there can be several types of nonlinear models. So what is a nonlinear model? A computer model which is damage aware, which has the capability to capture any inelastic action which we put that capability in it, right? So any damage, any inelasticity, for example material inelasticity, cracking, yielding, crushing, all those effect or behavior, if the model is able to predict or capture, then it is called a nonlinear model. On the other hand, a linear model doesn't have that capability. It is not damage aware. It follows F is equal to KU or Hooke's law forever, right? So in order to make that model damage aware, we have to give all the capacities in it as an input. We have to tell that program that all the beams will yield at what bending moment, all the columns will have shear failure at what shear force. So all the capacities at material level, at cross section level, at member level, they should be provided as an input in a nonlinear model. So which means that developing a nonlinear model requires far more inputs compared to a linear model. So I always make a comparison in the form of you can say inputs, required inputs. Just for an example, take an example of a material. Once you define the elastic modulus, one constant number, your elastic material is defined. a linear elastic computer model only requires elastic modulus and Poisson's ratio to completely define a material, because that model will be linear forever. So all it requires is the elastic modulus and Poisson's ratio. On the other hand, a nonlinear model requires a complete nonlinear stress strain curve of a material in order to completely define it, because the nonlinear model should have the capability to know that what will happen to our material at different load levels, when that material will crack, when that material will yield. That can only be defined using a complete nonlinear stress strain curve. So this is an example using which you can understand how much input is required to actually construct a nonlinear model. Similarly, take example of a simple beam. Let's say this is your beam and it is part of a detailed structural model, and the relationship between the bending moment and the result of that bending moment, which is cross-sectional curvature, for example. What is curvature? For example, if this is your beam elevation view, and because of some bending moment or applied loading, it bends like this, right? So the angle between a vertical line in the initial undeformed shape and the line in the same line when it is deformed in the bending shape, that is curvature. So if I just take one particular cross section, the line which was vertical AB before bending, it will not remain exactly vertical, it will shift to a new location A prime B prime, right? Because of that applied loading, or the result of that applied loading is the bending moment which will be produced, and because of that bending moment you will have a new position A prime B prime, and the angle between this initial vertical line and the new line, deflected line you can say, that angle is actually phi, right? So that angle is the curvature, generally represented by the symbol phi. So curvature is actually a cross-sectional deformation, which is the deformation associated with bending moment, right? So moment have an effect called curvature. So moment is related with curvature, just like stress is related with strain, right? Torque is related with twist angle, let's say theta. Similarly shear is related with shear force, is related with shear deformation. Moment is having a deformation which is curvature at cross section level and rotation at member level. So for one particular beam which is elastic, for example, we know already the elastic relationship between moment and curvature, and that is this: M is equal to E into I into phi. This is a classical bending formula which we know right from the start of strength of materials, right, or theory of structures, for example. So this is a classical expression which is having the same form: action is equal to some constant which is stiffness multiplied by deformation. So action is always related to its deformation using a constant called stiffness, right? Stress is equal to E into epsilon. Similarly, shear stress is equal to shear modulus times shear strain, right? So all the actions in a linear model are related to their deformations using constants which are called stiffnesses for those actions. A linear structural model is always characterized by those constants, right? So if this is a linear beam, all it requires is E and I for the elastic modulus for the elastic model to construct the K matrix, right? So it requires the elastic modulus of that material for which it is made of, and it also requires the moment of inertia, which is the function of cross sectional dimensions, right? So for elastic model you only need EI to define a beam, right? But for the same beam, if you want to make it nonlinear now, you need to define your own relationship between M and phi. No more m is equal to ei phi, right? If you plot a relationship between moment and phi, a linear equation will always be linear forever, and the slope will be ei, right? Just like stress strain curve, the slope is elastic modulus. Here the slope will be ei. But if you want to make this particular beam as non-linear or damage aware, then you have to give your own non-linear moment versus rotation or moment versus curvature behavior as an input in the structural model, so that the model knows that at what bending moment my this particular beam will yield, or at what bending moment it will have the ultimate failure, after which it will not take any more bending moment, or what will be the curvature or deformation associated with this particular action, right? So this complete curve has to be provided as an input in a nonlinear model. Compare it with now ei only. Ei means what? You just define E as a number and just define cross-sectional dimensions, program can calculate I, right? So, but here now you are responsible for whole this beam's behavior, and you will control that behavior using this complete curve. You will develop that separately, or take it from some reference, or you just use some experimental results of moment and curvature and then put it in the program as an input, right? Then program will be able to simulate that damage, where it will know that what is the bending moment corresponding to yield of that beam. Similarly, you can make it any shape. You can model cracking yielding ultimate moment. This is cracking moment, this is yielding moment, this is ultimate moment, then this is the last moment beyond which the beam should be considered completely gone, right? So this shape you have to provide as an input with all of its values, right? So member level or element level or material level behavior is in your hand in a nonlinear model, and then you apply loading to such a model and let it simulate any damage which the applied loading can produce, right? So it is a more detailed domain of modeling and analysis compared to linear model. So one more example, the role of reinforcement. There is no role of reinforcement in the linear analysis result, right? We know that already. In order for the program to develop the global K matrix of your structure, the program doesn't require your amount of steel, right? But for nonlinear model, it requires that amount of steel, because that steel will contribute to the capacity of your model, which is now an input, right? So we discussed in last lecture that capacity we have to provide, we can provide at different levels. The fundamental level is the material level, that we make our material nonlinear through the actual stress strain curves and let it manifest at the member level, cross section level, and then member level, and then full structure level, right? If we do that, we are actually following what we call as fiber modeling approach, right? Introducing the nonlinearity right at material level, right? But then on the other extreme we have what we call as the concentrated plasticity approach or lumped plasticity approach, and in that approach, instead of making material as nonlinear, we directly go to cross section or member level, higher level, and directly make a member as nonlinear using moment versus rotation curve or moment versus curvature curve. So instead of giving the material capacity, we directly give the member capacity. We tell the program directly that this beam will yield at this moment, instead of telling it that the concrete in that beam will fracture or will crack at this stress. So instead of giving the stress strain material as an input, stress strain curve as an input, nonlinear curve, we directly give the member capacity as an input. So program doesn't care about nonlinear materials, it directly knows that this is the bending moment at which this beam will yield, this is the shear force at which that column will crack or yield, or all other elements or so the capacity is directly defined at member level. So and there is also one approach in between them, which is called distributed plasticity, in which we can give the inelastic action to a certain length of the member. That can be the whole length of the member or just part of the length also. So these two approaches, fiber approach and plastic hinge approach or concentrated plastic hinge approach, we will be using these two approaches for further discussion. Continuum models, as we discussed in last session, that they are more detailed models and you may not use them for many practical cases, right? So this is the overall summary of that whole discussion. We did that in last class. In the concentrated plasticity approach, we actually define the nonlinearity at certain locations, not along the whole length, but at certain locations of the elements. We assume that it is concentrated only there.